Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. So today we will continue our lesson on Introductions to Scientific Programming, chapter 12, which is all about polynomial. So this is the objective for today's lesson. So after you learn about this chapter, you should be able to. The first one is you need to represent polynomial as vector. So in MATLAB, if you wanted to do some operation, you need to convert the polynomial expression into vector. So later on, I will show you some of the example and how you wanted to do it. Alright? So the second objective for today's lesson is to find polynomial roots. So in MATLAB, you can use the roots function to find the polynomial roots. Okay. So the third objective is you will be able to use MATLAB function to multiply and divide polynomials. And the fourth objective is you will use the polynomial to model a data through curve-fitting function, polyfit and polyval. Alright? Okay. So first, what is actually polynomial? So when we are learning about polynomial in this chapter, what is actually polynomial? So polynomial is actually a mathematical expression consisting the sum of many terms. Okay. So when we see the word polynomial itself, poly means many, nomial means terms. So it is directly represented by many terms. Alright. So it means that polynomial has many terms. So each of the term in polynomial consists a variable raised to a positive integer power and multiplied by a coefficient. So this is the example of the polynomial expression. Okay. So in this expression, there are four terms with x is the variable. Okay. So this is the variable x which represent the term for this polynomial. Okay. So from the right, each term has the variable raised to an increasing integer value start at 0. So in polynomial expression, it is actually start from the right hand side where the term will be multiplied by the power of 0. And then it will increase by 1 into the power of 1, the power of 2 until the maximum power of the term. Alright, so inside the expression itself, it has the coefficient where it represented by the value of a. Okay, so each term has their own coefficient. Okay. Alright, so next let's take a look at some of the application for polynomial. So the followings are common application of polynomial in electrical engineering. So we later on as an electrical engineer, we need to know what is the application of the knowledge that we have learned inside our degree. Okay, so this is some of the application for polynomial. So the polynomial can be used as system representation. So when you have a system, you can convert it into an equation or expression by using polynomial. So next is system stability evaluation. So you can also evaluate the stability of the system only by observing the characteristic of the polynomial expression of the system. Alright. So next is you will also be able to modeling the acquired data. So when you get the data, you can model the data if you wanted to improve the accuracy of the data. And the last one is you can do the calibration. So with the what we call the equation, polynomial equation that you get from the data, you can calibrate the data and also you can calibrate your sensors. Alright. Okay, next we will proceed to the vector representations. Okay, so what is actually vector representation and why we need to do vector representations? So polynomial coefficients are normally constants and can be grouped into a single vector. So usually the coefficient inside polynomial, it is actually what we call a constant. It doesn't have any variable value. It doesn't have, the value doesn't vary. Okay. So in MATLAB, the coefficient vector can be either in the form of row vector or column vector. So in terms of vector representation, you can actually customize your vector. Either you want your vector to be in terms of row or you want your vector to be in terms of column. Okay. Alright. So when you are converting into a vector representation from the polynomial terms, okay, MATLAB can provide many functions to work with polynomials. So right now, after you convert your polynomial expression into a vector, now MATLAB can read and it can operate and it can do some of the functions to your polynomial expression. Okay, So the function that will be covered in this chapter are as follows. Okay, so in this chapter we will be covered 5 different functions of polynomial. So the first function we call it conv. Okay, conv is all about polynomial multiplication. So if we wanted to multiply the polynomial expression, we will use conv. Okay, so the second function is deconv. So deconv is actually a polynomial division. So if we wanted to divide two polynomial division or two polynomial expression altogether, we can use deconv functions. Alright, so the third function that we will use is roots. So if you wanted to find the polynomial roots, we can use the function roots. And the next one is we wanted to use a polyval function if we wanted to evaluate the polynomial. For example, if we are given the value inside the term, we can find the output value of the equations. So in this MATLAB software, polyval is the function which is do that kind of work. Okay, so the last one that we will learn today is we will learn about polyfit, which is all about polynomial curve fitting. So if you already, for example, if you collected the data and you wanted to find the equations of the data, and if you wanted to find if you wanted to smoothen the data trend, you can use polyfit. All right, okay. So let's take a look at example number 1, which is all about vector representation. So example number 1 show you some of the example on how you wanted to convert from polynomial expression to vector representations. So basically from here, you can see here is that in order for you to convert from polynomial to vector, you only take the coefficient. Okay, so in order for you to what about the order? So the sorting of the coefficient of a vector representation, it will start from the right hand side, which represent x to the power of 0. So 1 is the coefficient which represent x to the power of 0. 0.5 is the coefficient that represent x to the power of 1. 2 is the coefficient which represent x to the power of 2, and so on. Okay, so it will start at x to the power of 0. Okay, you put the coefficient inside the matrix. Okay, but what about the polynomial expression that doesn't have any any coefficient that represent for example, this one a to the power of 0, there are no coefficient, but you must start at a to the power of 0 from the right hand side. So to solve this kind of problem, you can just put 0 inside the matrix. Okay, so this 0 represent a to the power of 0, 0 represent a to the power of 1, 0 represent a to the power of 2, and 1 represent a to the power of 3 here. Alright, okay, so if you wanted to convert from polynomial expression to vector representation, you must start with the right hand side, where the power of the term will start from the power of 0, and on the most left hand side, the power of the term will end at the highest or the maximum power of the term. Okay, so the value that you need to put inside the vector is the the coefficient for the polynomial. Alright, so next is conv and deconv, okay, which is all about multiplications and also the division for polynomial. So the syntax for conv and deconv, okay, so first we'll take a look at the syntax for the conv. So this is the example, w equals to conv u v. So it means that if you have two polynomial expression of u and also v, if you wanted to multiply it together, you can use this function conv u and v. So it will multiply vector u and vector v. Okay, so next is the division. So wr is actually equals to deconv uv. So if you wanted to divide the expression u by v, you will get the output of w and r. So w is actually the polynomial division of vector u over vector v, and r is the remainder. Okay, w is the polynomial division of vector u over vector v, and r is the remainder. Okay, so later on I will show you some of the example for multiplication and division. Okay, so now let's take a look at example number 2. So this is example 2, which shows two different operation. Okay, so this is the polynomial expression x to the power of 3 plus 3x to the power of 2 plus 2 multiplied by x to the power of 2 minus 5, and this one, the expression is similar, but the operation is different. So this one is multiplication and this one is division. Okay, so this is how you wanted to find the multiplication and divisions for the polynomial expression. So first, what you need to do is you need to convert this expression into vector. So what you should do is you should start from the most right hand side, which has x to the power of 0. Okay, so this one have 2 represent x to the power of 0. We doesn't have any term represent x to the power of 1 here, so you can just put 0 here. So you have coefficient of x to the power of 2, you put 3 here, and this is x to the power of 3, so the coefficient here is 1. Okay, so similar with the second expression. All right. Okay, so right now you get f equals to conv ab, so it means that it will multiply a and b all together, and you will get this answer: 1, 3, -5, -13, 0, and 10. So this is actually the coefficient for your polynomial expression. It will start from the left hand side, which is the highest term power, and it will end at the most right hand side, which will represent the lowest term power, which is the power of 0. Okay, so next is the division. Okay, so division is represented by we store the value of g and r here. G is the multiplication output and r is the remainder. So you wanted to divide a and b all together. Okay, so right now you get g 1, 3 and r equals to 0, 0, 5 and 17. Okay, so for these division problems, okay, 1 represent the for g, okay, for the expression g, 3 represent the lowest power of the term, and 1 represent the highest because it only has 2 terms, right? But for r, this expression you need to divide again from this one. If this expression divided by x squared minus 5, the remainder will be divided again by x squared minus 5. For example, this one. 1 here represent x, 3 here represent number 3 here, and then 17 here represent by 17, and 5 here represent by 5x because this represent x to the power of 1, right? So this one represent x to the power of 0. And then all of the remainder terms will be divided by the x squared minus 5, which is, you get it from here. Okay, so you need to do it that way. All right. Okay, so next is system representations. Okay, so many engineering related systems can be represented with mathematical model, and polynomial is one of the mathematical expression commonly used to represent the system, especially for electrical and electronic systems. So actually there are many types of mathematical expression which is used, but polynomial is one of the expression which is commonly used to represent a system with mathematical model. Okay, so one case is when a system is represented in Laplace domain, where we use the term s as the polynomial variable. So this polynomial representation of the system is called the system function. So if you represent a system with an equations, so it is called a system function. So other than that, polynomial can also be used to represent signal or data. Okay, so if you have the data, you wanted to convert the data into an equation, you can use polynomial expression also. All right. Okay, so let's take a look at example number 3. So in this example, figure below shows a system with PID controller GS. So we have a PID controller, what they call expression here, GS equals to ds squared plus ps plus I over s. So this controller is used to stabilize the plant HS. So we have the equation of HS here. For example, motor, car acceleration pedal, or compressor. So the overall system function of the system is QS. So all of this is the system, which consists of a controller GS and also the plant HS, and all of the system here represented by QS. Okay. So Qn is denoted as numerator of polynomial and Qd is the denominator. So in Qs, Qn is the numerator equations, and Qd is the denominator. So d, p and I is the PID controller constant. Okay. So now let's say we wanted to control a motor at a specific speed. So now we have a situation where we wanted to control a motor at a specific speed. where the motor can be represented by using a polynomial hs 1 over s minus 2. So right now, they already give it to you the equation for the plant, okay? So we have a typo here, so this is actually 1 over s minus 2, I'm sorry, okay? So below is the MATLAB code to generate the two polynomial qn and qd. So in this example, we set p equals to 4, d equals to 2, and I equals to 1. So let's say p equals to 4, d equals to 2, and I equals to 1. Okay, so what you should do first is you must convert your polynomial expression into a vector. Okay, so gn is here, gn. You convert it into dpi. So this is d, this is p, this is I. 2, 4, 1. Okay, 2, 4, 2, 1, 2, 4, 1. Okay, and then gd here says that as, okay, because we need to start it from the term which is the power of 0. You must put 0 here, and 1 which is represented by s, and then hn is given here 1. Okay, 1 here, and hd, this is a vector for hd, 1 which is represented by s, minus 2 which is represent s minus 2. Okay, this is minus 2. All right, so qn is actually the multiplication for the what we call hn. Okay, qn you will get to s square, okay, plus 4s plus 1, which is the when you go back to this one, so qn is actually gn hn, so gn multiplied by hn. Okay, and qd is equals to gd, so gd here multiplied by hd plus the same term as above. Okay, so you will get these answers. All right, so qd will become 3s2 plus 2s plus 1. Okay, so you can test this coding in order for you to further understand about system function. Okay, all right, so next we will learn about polyval. So what is actually polyval? So the syntax for polyval is polyval p and x. So what is actually p and x? So p is actually polynomial coefficient specified as a vector. So p is the polynomial expression, but you already convert it into a vector. So you must convert it into a vector. All right, so x is the evaluated points and y is the output, which is the evaluated value. So polyval is actually the function that we wanted to get the output of polynomial expression where we are given the value of the terms. All right, so for example, find the function of x to the power of 3 plus 4x to the power of 2 minus 2x plus 1 for x to the power of x equals to 3.5. Okay, so in this example, you are given the value of x and you wanted to find the output of x. So what you should do is, first you must convert this expression into vector representation, and then you can directly use polyval. Okay, so this is the variable that stores the output, and then this is the function polyval. This is expression p that has been converted into a vector, and this is the value of your term, okay, 3.5, and then you can get your answer. All right, so next let's take a look at example number 5, which is all about frequency response. Okay, so we can so for this example, you can go back to example number 3, where numerator and denominator polynomial is used to represent a system where qs equals to qn plus qn divided by qd. So in example 3, we already find the equation for a system which represented by the term of qs. Okay, so to understand the system, the polynomial is evaluated over a range of s values. Okay, so right now we wanted to find the output of the system at certain s values. Okay, so in this case, s is represented by j2 pi f, where f is the frequency in hertz. Okay, so right now your input s is given as j2 pi f. Okay, thus the value of f must be first determined to have the s value. So here we set f from 0 to 10 kilohertz. Okay, so right now j2 is a value, pi is a value, what do you call the fixed value, and f is the value that we need to define. Okay, so right now we wanted to define f, which is start from 0 hertz to 10 kilohertz. All right, and lastly, a graph is plotted to visualize the behavior of the system. So lastly we will generate a graph. Okay, so this is the coding. Okay, so qn and qd, so this what do you call this vector, we already get it based on the example number 3. So you can go back to example number 3 and you can see how we wanted to get qn and qd. vector. All right, and then this is the f value, which is start from 0 until 10 kilo. Okay, and s is actually the value of the term. Okay, so if we wanted to evaluate the polynomial expression, we need to know what is the value inside the term. Okay, so right now the term is s, so s is represented by, okay, 1i multiplied by 2 multiplied by pi multiplied by f. Okay, so f is the frequency. So q and s, okay, so the evaluation of qn is actually polyval qn, the expression of qn over s. Okay, qds is actually, we wanted to evaluate the value of the denominator of the system. Okay, qd comma s, and this is the output of qs. Qs equals to q and s, this one, okay, dot divided by qds. Okay, so this is the output of the system, qns over qds. Okay, qs equals to qn over qd. This is presented by here. And then here you are using semi-log because the range for the frequency is quite far. It is start from 0 to 10,000 kilohertz, 10,000 hertz. So the value are too far. So you need to use semi-log graph. Okay, so you can just label and give the title. All right. So HN and HD were created from example 12. So this oh, I'm sorry, this one is not valid actually. So this is actually QN and QD were created from example 3. Okay, and semi-log x plot is used to plot the data because the range of f is very wide. Okay, all right, so this is the output that you can get, which is the frequency response. This is the magnitude and this is the frequency. All right, okay, so next we will learn about roots. So what is actually roots inside polynomial expression and how we wanted to find it. So in polynomial expression, the roots of polynomial is all x values, which is the term values that return px equals to 0. So actually the roots is actually the value of term where the output is equals to 0. So polynomial with its highest power equals to n will have n roots. For example, the highest power for polynomial is 2. So it will have 2 total roots and so on. Okay. So the syntax for to find the roots is just simple. Y is the variable that stores the the roots, okay, the roots value and roots, and p is the polynomial vector, okay, because you need to convert it into vector in order for you to operate inside MATLAB. All right, so in example number 6, let's take a look at example number 6. Example number 6 asks you to find roots for polynomial fx equals to x to the power of 3 plus x to the power of 2 minus 4x and minus 4. So what should you do first? Okay, so first what you should do is you should convert the expression into vector. Okay, 1 1 minus 4 minus 4. Okay, and then you can just simply use roots. Okay, r equals to roots p, which is this expression, and you can get the roots. Okay, so from here you can see that the highest power of the term is 3, so you will have 3 total roots. All right, okay, so now let's take a look at example number 7, which is all about vertical displacement. So it is actually the application of the roots inside polynomial. Okay, so example number 7, launch an object from ground vertically, okay, and find out how long will it take to hit back the ground. So when you it's like you are launching an object from the ground, and then you wanted to see and you wanted to observe and you wanted to record what is the time that the object will hit back the ground and it will fall back to the ground. Okay, so the formula for vertical displacement is as below, where v is the initial velocity and g is the acceleration due to gravity. So let's set the v equals to 30 millisecond minus 1 and g equals to negative 9.8 millisecond negative 2. Okay, so this is the formula. Okay, you can see is that this is d, which is the distance, velocity and time, plus g over 2 multiplied by time square. Okay, so t is actually your term, v g over 2 is actually your coefficient. All right, okay, so this problem can be solved by finding roots of polynomial since ground is where d equals to 0. So this problem can be solved by using finding roots, because d equals to 0 represent when the object reaches the ground. All right, so we wanted to find the t, so you can just use the roots. Okay, so first and foremost, what you should do is you should convert this expression into a vector, and then you find the roots. Okay, so this is actually the expression for you to find either it is on the ground or not. Okay, so this is the time, and this is the evaluation of the points of the distance, because we wanted to compute a trajectory of the distance from the object to the ground. Okay, with time. Okay, time from 0 until it reaches the ground. Okay, with the difference of 0.01. so this is the polyval, which is the evaluation of the polynomial. All right, so you will get this kind of output. So this is the vertical displacement. It starts from displacement 0 because it starts from the ground and the time is not ticking yet. And then you throw away the object, and then the time will start ticking. So the object will move like this, and then it will fall back. Okay, and then when it falls to the ground, which is displaced by the displacement of 0, this is the time where it hits the ground. All right, so you wanted to compute this kind of output. All right, so you can do it this way. Okay, all right. So next example is the system stability. So previously I already shows and I already tell you one of the application for polynomial is to test the system stability. Okay, so this is the example for this application. All right, so for system stability, example number 8. So back to example number 3. So for this example, you need to go back to example number 3. So the stability of the system represented by polynomial can be checked by the roots value of the denominator polynomial QD. So when you have the equations of the system, you can observe the stability of the system if by observing the denominator part. Okay, so a system is stable if all of the denominator roots are less than 0. Okay, so when you are taking the denominator part of the system, you need to find the roots of the denominator. So if the roots are less than 0, so it means that your system is stable. Okay, so now create a MATLAB functions that check the stability of the PID control system described in example 3. The input variables to the function are as below, while the output variable is none. So constant PID specified as vector C equals to PID. Numerator polynomial of the plant specified in vector Pn. Denominator is specified by vector PD. Apart from the above, the function should display at command window the roots and string message on whether the system is stable or not stable. Okay, so this example wanted you to create a function to detect either the system is stable or not. Okay, right. So this is the MATLAB function for example number 8. So this is a function, check stability, the function name, input of C, input of Pn, and input of PD. So you C is actually you wanted to this one, the PID. Okay, C is actually the PID parameter. So C3 is P, C1 is I, C2 is D, or C2 is this one is DPI. Okay, and GD is 10, so GD is the denominator. All right, okay, HN is you can just refer to the what you call to the previous example 3 to see what is actually this one. Okay, GN, GD, HN, and HD is already described inside example number 3. Okay, so next we wanted to find the roots for HD, which is the denominator for the system. Okay, okay, when we find the roots, we find the length of the root. Okay, and if root is greater or equals to 0, so it means that the system is not stable. Okay, all right, so R, for example, R equals to root multiplied by roots we will call greater or equals to 0. If it's empty, it means that if this one is not correct, so it means that the system is stable. So it means that if R is less than 0, the system is stable, else the system is not stable. Okay, so this is how you can create the MATLAB function to detect the stability of the system. Okay, right, so this is how the MATLAB code is used by using the check stability function for several values of PID and different plants. Okay, so you can see here is that This is the check stability function that we already initialized in example 8. So this is how we can use it. Okay, check stability, and this is the parameter PID, and this is actually the, what do we call, the coefficients of all of the denominator and numerator. Okay, so you can see is that it will find the root of 1 and root 2. So both roots are less than 1, so the system is stable. Okay, so when we give this kind of values, the root that we get is 0.17 plus 0.55i. So it means that the system is not stable because it is greater than 0. Okay. Alright, so this is the third example when the first root is 0, the second and third root is less than 1. Less than 0. So it means that the system is stable. Okay, so you can try the code by yourself, and you can learn on how you wanted to check the system stabilities of polynomial expression. Okay, so if you have the equations of the system, if you already create this function, so you can simply check your system stability. All right, but you need to make sure that the expression must be in the same form. Okay. Alright, so next we'll take a look at polyfit. Okay, so what is actually polyfit? So polyfit is represented by output P equals to polyfit x, y, and n. So the description for this syntax is x is the x-axis data, y is the y-axis data, and n is the degree of the polynomial fit, and p is the least square fit polynomial coefficient written as a vector. Okay, so polyfit is actually we wanted to find the polynomial expression of the data. Okay, so we have x-axis data and y-axis data, and from the data we wanted to find the expression. For example, if we wanted to smoothen out the data, okay, and n is the degree of the polynomial fit, so it is actually like the resolution for the fitting process. All right, so the higher the n, the higher the accuracy, but sometimes it doesn't work like that. Okay, so you can try it by yourself, and you can see what will happen if you increase the value of n, which is the degree of polynomial fit. All right, so curve fitting. So curve fitting is the process of constructing a curve to a series of collected data points. So if you already collect some data, you can curve fit it. Okay, so the curve is represented by mathematical functions such as polynomial. So if you have a curving line, so it is actually represented by a polynomial expression. Okay, so the idea of having the curve represented by a mathematical function is a way to model a process or activity that varies over some variables. So the idea, if you have the curve, so how you wanted to translate the curve into a what you call mathematical expression, you can use polynomial. So that is the answer. All right. So for example, if you wanted to model a yearly climate data or model an internet usage, you can use the polynomial expression to model those kind of curve or those kind of data. All right. So why modeling? So you need to model those kind of data because you wanted to automate your process. Okay, so automation is all about you wanted to estimate, right, what is the output or what is the next condition that will be happen to the system. Okay, so next is you wanted to analyze the relationship between variables. So if you have some variables and you wanted to find the relationship, so for example, if this one is increasing, what about that one? What is the relationship between A and B? But if A is decreasing, what will happen to the B? You wanted to analyze that kind of relationship. Okay, and the third part is the data trend. So the data trend is actually very important because you wanted to estimate, okay, what is actually the condition that will be happen when this input is given or when this situation is happening. Okay, so you need to know what is the data trend. All right, so next we'll take a look at example number 9, which is all about sensor calibration. So for this example, the spreadsheet chapter 12, example 12_3 will be given to you. So I will ask from the coordinator, and after I got this file, I will give it to you. Okay, so this spreadsheet contains a temperature sensor reading in volt taken over temperature between 20 degrees Celsius to 50 degrees Celsius. So find a mathematical function. So this example wants you to find a mathematical function from the data, okay, that will convert the sensor reading from volt to temperature. Alright, so the solution from this example is finding mathematical function to a sensor reading is normally done to calibrate the sensor. Okay, so usually if we wanted to calibrate the sensor, we need to find the expression or the equation for the data first. Okay, and then we can calibrate the sensor. Okay, so sensor calibration is important to ensure accurate reading. Yeah, that's why we do the calibration. So in this example, the calibration can be done by applying polynomial curve fitting to the collected data. So in this example, we will be using polynomial curve fitting. Okay. So in MATLAB, function polyfit is used to obtain mathematical function, and then we use polyval to test the output. So polyfit is used to obtain the mathematical function from the data, and then we use polyval to test the output of the equation that we get. So is it accurate or not? Okay. Right, so below is the MATLAB code to obtain the mathematical function using polynomial curve fitting function. So based on the collected data, the polynomial order is chosen equals to 1. Alright, so this is all about, you wanted to read the Excel file, you already learned it in the previous chapter, and this is how you wanted to extract the data. This is the voltage and this is the temperature. Okay, so P is actually polyfit. Okay, we wanted to find the expression of the data. Okay, so this is the x-axis, which is V, the y-axis, which is the temperature, and this is the N. Okay, we are using the order of 1. Alright, and then this is we wanted to evaluate the data. Okay, by using ST. Okay, ST equals to polyval. We wanted to evaluate P, V. Okay, so we wanted to evaluate the expression P that we get. In this here we will get polynomial expression. Okay, and here we wanted to evaluate either the expression is true or not, or it is accurate or not. Okay, all right, and then the input that we give it to the what you call the polynomial expression P is the voltage. Okay, and then you will get the answer here. So you see here, this is the blue X mark here, is that it shows the collected data. Okay, and then the what do you call the orange line here shows the data, shows the curve that you get from the mathematical expression. Okay, so first, in polynomial curve fitting, first you have the data, right, which is represented by the X mark here. Okay, and then you need to find the mathematical expression of the data. Okay, the mark, the blue mark here, the blue X mark here. Okay, after you find the expression, you want to evaluate, is it the correct expression? So is it accurate or not? So what you should do is you should put the value of the input, which is the sensor reading, inside the expression. Okay, and then you evaluate the curve, or you evaluate the expression that you get from polyfit. Okay, by using the function of polyval, and this is what you get. Alright, so from here you can say here is that the equation that you get from the polyfit is accurate because it is nearly what do you call dominate some of the data that you have been collected. Okay, so the trend is similar. All right, okay, so next we will take a look at example number 10. So example number 10 is a table of 6-month internet usage for 5 persons of age above 30 that previously never used an internet. So find the usage trend and estimate the internet usage at month 7, 8, and 9. So this data is available in the file internet usage.xlxx. So this is actually, I think you can do it by yourself because the data is already here, right? Okay, if I get this file from the coordinator, I will give it to you, alright? Okay, so the data trend can be obtained by fitting the data by using polynomial. So previously I already told it to you, right? If you have the data and you wanted to get the equation from the data, you can use polyfit. Okay, and after that, if you wanted to evaluate either the expression that you get is accurate or not, you can use polyval. Okay, so this is what we do here. So this is we wanted to read from the Excel file, we wanted to extract the data, and we wanted to extract the month. Okay, so this is actually the internet quota, right? So because this example is all about internet quota. Okay, so this is the month. Okay, so P1, P2, and P3 is different expression that we get to evaluate the data pattern. Okay, so P1, P2, and P3 is represent the expression because we wanted to take a look at the degree of accuracy. Okay, the first one we put order 1, the second we put it order 2, and the third expression we put the order number 3. Okay, so we wanted to observe what will happen if we increase the order. Is it more accurate or is it not? Okay, so this one is actually we wanted to evaluate the expression that we get. This is P1 represent the order number 1, P2 represent order number 2, P3 represent order number 3, and data fit 1 represent the evaluation for P1, data fit 2 will represent the evaluation for P2, and data fit 3 will represent the evaluation for P3. Okay, okay, so this is what you get. Okay, so the data is represented by the blue circle here. All right, okay, the first order is the orange one, the second order is the yellow one, and the third order is the purple one. Okay, all right, so actually for that you can see here is that the second and third order is actually like overlapping each other. So from the above figure, second and third order polynomial fitting are more accurate to represent the data compared to the first order polynomial. Okay, you see the first order polynomial is not as accurate as the second and third order, which is represented here, because the distance between the curve to the data is quite far, right? But for second and third order here, that represented by this line, is quite similar. The trend is quite similar. Okay, so we can say here is that second and third order is more accurate than the first order, because the first order doesn't exactly follow the trend of the data. Alright, therefore the second order polynomial is chosen as the mathematical model of the data trend. But this time we are choosing second order, not the third order. Why? Because the higher the order of the polynomial curve fitting, the higher the computational cost. Okay, so because we wanted to reduce the computational cost, we need to select the second order, because second order and third order the output is the same. So why we need to choose third order? We can just choose the second order because it has lower computational cost. All right. Okay, so to find the internet usage for months 7, 8, and 9, so the question also asks you to find the internet usage for 7, 8, and 9 a month. So polyval function is used with the evaluated point set equals to a vector of 7, 8, and 9. So you can just use polyval function to evaluate your what do we call the internet usage. Okay, you already have the trend. Okay, and then you wanted to estimate what is the internet usage for the next month. Okay, so what you can do is you need to use polyval. Okay, evaluation of polynomial expression. All right, so here you can see here is that we are choosing P2 because P2 is more accurate with less computational cost. All right, so this is the month 7, month 8, and month 9. Okay, and then you will get the output like this. All right, okay, so next is example 11. So example 11 is all about a farmer want to automate the irrigation system for his crops so that he will never have to change the amount of water setting to the irrigation system every day. So this problem is a farmer, they wanted to automate the irrigation system. He doesn't want to give the water to the plant manually. He just wants to automate the system. Okay, based on the data he collected on the water usage of the previous crop cycle. So in the previous crop cycle, when for example, he planted some tomato, right? And he collect the data and he observed the trend of the data on the water usage. Okay. So this question asks you to find a mathematical formulation from the data. Okay, so this formula will be used as the basis of the automatic irrigation system. So this question asks you to find the equation of a data, and they want you to estimate what is the water requirement for the plant later on. Okay, so the water usage data can be found in the file waterusage.xlxx. So as usual, I will request this file from the coordinator and I will give it to you. Okay, so the solution in this example, we will do the curve fitting using several degrees of polynomials and pick the best for the water usage data based on the measure called R squared, shown by below equations. So DI is the measured data and FI is the fitted data. So for this example, we are using r squared. Okay, r squared is actually equals to 1 minus the summation of di. Di is the measured data, and fi is the fitted data over the summation of the measured data squared. So this is one of the what do you call a curve fitting methods, which is called r square method. Okay, all right. So but first thing first, we need to find the expression which is the fi first. Okay, the fitted data. All right. So MATLAB code for this example. Okay, so for the first part is we wanted to read the Excel file and we wanted to extract the data. So n equals to 5. So you can study this coding, okay, because all of what it does is we wanted to find the most. N equals to 5 is because we wanted to find the most accurate curve fitting. Okay, we will start from degree equals to 1 until degree equals to 5. Okay, we are observing 5 different degrees of polynomial and we will choose the best one. All right, and after that we are using that the chosen polynomial expression will be used to compare to the measured data. This one, it will become fi. Okay, and di is the measured data that we get, that the farmers get. Fi is the data that we get from the polynomial expression. All right, and then so this is the output that you get. So below are the displayed information at command window. Okay, so r squared value is actually the more accurate way for you to observe the accuracy for your what do we call for your order of the system. Okay, okay, you see here, I'm sorry, from here. Okay, in this coding, okay, so first this loop, it is used to find the polynomial expression for 5 different degree. Okay, and then we wanted to evaluate the data. Okay, and after that r2 here is used to find the accuracy of the equation that you get. Okay, so this is your output. So for order 1, the accuracy that you get is 0.9953. For polynomial number 2, the accuracy that you get is 0.9954. And for polynomial order 5, you will get the accuracy of 0.9994. It is so accurate for polynomial order 5. So since the r square value for the third order polynomial, which is equals to 0.9991, can be considered as good enough. So it is actually good enough because 0.9991 is actually 99.91. So it is actually good enough to become accurate. Okay, because the higher the order, the complex the system, the higher the computational cost. We doesn't want to have that kind of things. Okay, all right. So thus the best polynomial order is 3 in order to keep the complexity of the polynomial low. Okay, thus the chosen polynomial is as below. So p33, so this is the equation that you will get. Okay, so w, which is the water, is equals to this expression, this polynomial expression. Okay, so later on, if you have the questions and they ask you to use r square to measure the accuracy of the system, you can refer to this formula. R square equals to 1 minus the summation of di, which is the measured data, minus fi, which is the fitted data. After you get the equation, you evaluate it, you will get fi, and then this is the di square, which is the measured data square. Okay, all right, so this is the output that you will get. Okay, so x mark is representing the measured data. Okay, the orange is the order 1, the what do you call, the yellow order 2, the purple order 3, the green order 4, and the light blue is order 5. Okay, so you can see here the most accurate is actually order 5, but order 3 is only slightly less accuracy, but you know, you can see here that the slight what do you call, the slight accuracy difference is just only a little, so it is accepted to become the most accurate. Okay, all right, so I think that's all for today's class. So if you have any question, you can just ask me in the WhatsApp group as usual, or you can just email me. Okay, so I think that's all for today's class. Thank you for your cooperation, and Assalamualaikum.